Hello and welcome to the C programming lecture on pointers. So what is a pointer? Up until this point, we've kind of briefly talked about what pointers are without giving a real clear description. Well, a pointer is a variable that contains a memory address. Recall that all variables are stored at a particular memory address. So it turns out that pointers themselves also have their own memory addresses, but the value that they contain are actual memory addresses. So that sentence in and of itself can seem quite confusing at first. So let me just draw a quick comparison here. When you have a character, the value that it stores is a particular character. That type knows that it is a character. Now, when a pointer, or let's say a pointer to a character, its value is not a character. However, it is a memory address, the actual address for a variable that contains a character. So we're going to see a lot more examples over the next few slides of what that means. So in order to get the value out of a memory address contained within a pointer, we have to do something called dereferencing. So typically there's two different symbols. We have this one star here and this arrow. Depending on which context that you're using the pointer in, it will depend on which one of these you use. So a pointer has a data type associated with it, just kind of like the example that I gave you, and it just tells the program how to interpret the data stored at that particular memory address. So here is a very simple example of a pointer. So let's go ahead and go through this. First, our x variable is declared. We have the value 10 assigned to it. So next, inside line 7, we are actually declaring a pointer. And the syntax for that, again, is this pointer symbol, this little star symbol here in front of our variable name. So the variable name is actually pointer, and the star just indicates that it is a memory address that it is pointing to. And recall from one of our prior lectures, we went into the address of operator. So x actually has an address, and we assign the value to the variable pointer, the address of x. So I know that is confusing, but let's just keep going through. On line 9, we have the output of x. X prints out the value that is stored at x. So this is what occurs at line 9. Line 10 then prints out the address of x. So on line 12, which is our next output line, we see that we have the star symbol in front of the pointer. And what that's going to do, that's actually going to dereference, which is what I referred to in the prior side. That is actually going to dereference the value of the memory address stored in the pointer variable. So we can see here it actually has, when I say pointer value, it actually equals 10, which is the value at x. Now the address of pointer, when I do the address symbol, its own variable address is different than the x variable address. And that makes sense, right? It needs to have its own memory location regardless of what type it stores. Now we can see that the actual value that the pointer variable contains is a address. And if we read this address off, it actually matches the x address here. And this is the last output line here on line 14 in our program. So again, I would type this out and just kind of like reason about what's going on here. But again, just draw parallels. This last line here, this pointer variable, when we just print it out by itself, the value that it's printing out is actually the address of x. Okay. So up until this point, we haven't really discussed really what null is. So in the context of CM pointers, a null value is typically defined as 0, or a typecasted version of this is some type of 0 preprocessor statement that has been created in order to properly give you some equality checks. It's common to initialize the pointers to a value of null. So whenever you're using pointers, the default value will be null, usually. And or you will see people explicitly set it to null. So dereferencing a null pointer can cause your program to crash. So this is very important. Typically, these are referred to as segmentation faults or access violations. So your program will actually crash if you dereference a null pointer. So here is an example of this. We have the variable x here, and we have our pointer. So again, x is 10, pointer is set, you can see here explicitly to null. I then assign x, I assign the pointer value to the address of x. And we can see that here that everything's printing out just fine. This is working as expected. But then on line 12, I set the pointer value equal to null again. And we can see that I output, and we're saying setting the pointer null, going to deref and crash the program. So that is exactly what happens at line 16. And we can see here on the output, it says segmentation fault and core dump. We don't have to worry too much about this last part, but basically know that a core dump allows you to see specific things that were occurring inside of your program before it crashed. So anyways, dereferencing this particular pointer caused our computer program to segmentation fault. So what is a size of a pointer? This is a great question. All pointers will have some type of default size, regardless of the type associated with it. So unlike our prior examples where we had a character that may have been some types, let's say one byte, and then we had an integer, let's say that the integer was 4 bytes. So with pointers, the value is actually on the actual platform is going to be the maximum addressable space. So what does that mean? Well, in the context of a 32-bit operating system, your pointer values will be 4 bytes because you have a 32-bit memory allocation space. So your maximum memory addressable space will be 32 bits or 4 bytes. And on a more modern day computer, which is typically 64-bit or 8 bytes, the operating system will have a complete addressable space of 8 bytes. So nowadays it's common for pointer sizes to be 8 bytes on a x86, x64 processor. So the compiler will determine the default byte size of a pointer. And this is also dependent on how a program is compiled, either 32, 64. There's various different ways, and these can be interpreted as. But basically, it's just how much memory can your particular platform actually address. So this is an important distinction to be aware of, because the size of an addressable memory is vastly different between 32-bit and 64. So if you ever need to question about it, it's really simple to just write a quick program to figure out what your pointer size is. So here is a quick example of that. So you can see that I created a bunch of different types of pointers, and you can see on our output, every single one of those outputs a 8. And just like I said before, all the pointer sizes are going to be the same because it's the maximum addressable space on my particular system. Now, if I had a 32-bit system, we'd see that cut in half. So I would type this out and just kind of get familiar again. We can see that I'm passing in all the size of operators. These are P1 through P6, which are all of these particular pointers here. We're setting them all to null. It doesn't matter. We're not dereferencing them, so this program will not crash. So what is a void pointer? So we talked about this a few times already, but a void pointer is a pointer that has no data type associated with it. We can use this void pointer as a quote-unquote generic pointer. So don't get confused with other terms and other programming languages. If you've been exposed to it, this is not a generic. I'm just using this term generic to say that it's a box that can be just transformed into something else. And really, at the end of the day, any pointer can be that, but a void pointer specifically indicates that we expect a type to be, that particular pointer to be casted to another type in order for operations to occur on it. So let's go ahead and unpack the void pointer casting. So a cast is necessary in order to properly interpret the underlying data to a void pointer. So let's say that we have some void pointer P, and in that what we need to do is cast it to some type. In this particular instance, we're going to cast it to an integer pointer type, and then we're going to dereference that at the end. Remember that there's a particular precedence when we do these particular operations. So in this order, what happens is that the P1 gets interpreted as a int pointer and then is dereferenced later as that. So the data is reinterpreted as an integer. So here's another fun fact. Arrays are actually pointers. So it turns out that arrays and how we've been indexing them is just another way of doing a particular thing called a pointer arithmetic. So what is happening here is we have a x variable, and that has 5 slots inside of our array, so 5 elements. And we just created a quick for loop here, and we're looping over every element. And all we're doing here is we have our x variable and we have our I variable. And what that's doing is it has an offset. So we can actually say, okay, from x, add 1 to it. And what does that 1 mean in this context? Well, the 1 needs to be multiplied by the amount of bytes offset. So like in this particular case, every single element is actually offset by 4 bytes because every element is every integer is 4 bytes long. So when we add 1, it's really just, you can think of it as just multiplying it by a particular value as well. We can expand this and go even further into it, but at the end of the day, it all does the same thing as far as indexing is concerned inside of an array. So this is just showing you that we can use pointers with particular indexes and dereferences in order to actually access our individual elements inside of arrays. Okay, so in order to recap this particular topic, we've kind of talked about it in prior lectures, but just to drive home some points, pointers are variables that store another variable's memory address. That's it. That's really nothing more to it. There's tricky things that you can do with them, but at the end of the day, pointers, again, are just variables that store another variable's memory address. Pointers themselves have their own particular memory address. That's important. So a pointer has its own memory address, just like a regular variable. So a pointer type determines how to dereference and interpret the underlying data to a pointer. This is also important. So when you have a int pointer versus a char pointer, depending on how you have those, declared, it's going to depend on like how, when you dereference it, what the output is going to be of that particular variable. So yeah, just remember that basically when you declare a type of pointer, just make sure it's the type that you expect. So null is another way to express a 0 value for a pointer, and dereferencing null can cause a program to crash. So pointer's default size will depend on how a program was compiled or what operating system you're using. A void pointer is another way to store any type of pointer and later cast it to some appropriate type. It's usually used because you explicitly expect something to be cast to another type, because you cannot dereference a void pointer as it doesn't have any context in how to actually interpret it, because it is a pointer to nothing, which sounds weird. A pointer to a type of nothing, if that makes sense. Not a pointer to nothing, a pointer to a type of nothing. So let's go ahead and just hop into some code here and just mess around with some of these pointers. Okay, let's go ahead and get started by doing our usual stuff here, just because I want to stay fairly consistent in how I do these coding examples for just to build consistency. So again, we're just making sure our tooling's working by just writing a simple hello world program here. Okay, so that's working. All of our tooling's working. We're going to go ahead and save this and delete that line, save it. And we can just go ahead and start messing around with some pointers. So let's just make a int pointer. We'll set it to null. And what we're going to do is let's go ahead and make let's go with the kind of the same flow here that we had, which was making a char variable. Let's set it to the capital letter A. Let's actually set it to exclamation point. We remember call this is 33 as an integer. So what we can do is we can print out our char variable. Let's go ahead and do that with the address P. So we're going to do C and then address P. Let's go ahead and add a new line. Something like that. Okay, so there we go. And next what we're going to do is we're going to grab this guy and we're just going to go ahead and print out X here. So X and X, and the value should be null. So let's see, this will actually show us that, right? So it says the value is 0 at X currently, and here is this particular address. So now what we're going to do is we're going to say, okay, reassign this and re-output. Reassign X to the address of C, and I want you to re-output the last same line. So what's happening here is you can see that it's an incompatible type, it says. And this is just a warning, so it's not necessarily an incompatible type, but we will see. You see, may not see. And you see this is some negative value because it's actually, this actually needs to be a P, like so. Nil, okay, yeah, that's what we expected. Okay, great. So the actual address that's associated with it now, even though we got a warning, is actually the address of our C variable. So when we actually dereference this now, X deref, and we do a, so we know it's a character. So we could do a %C, or better yet, we could just do a D because we know that this is a int pointer and we can just pass in the deref to X here. Let's see, we're gonna ignore that warning and output, and we can see that it's some obscure value. So it doesn't appear to be interpreting quite what we expected. Defer. Deref. There we go. BC may not see. Okay, great. So let's go ahead and kind of reason about what's going on here. All right, so our first line here, we have a C variable, which is declared on line 6. We're outputting the address, which is here. Everything seems good. So we have, this is the actual integer value because we have %D. This is, everything's as we expect it to be. Here is the actual address of X, which is at the end, and then the value that it points to, which is nothing right now. And then on line 10, we actually assign a address to X. So we can see here that the address of X has been assigned, or I'm sorry, the address of C has been assigned to X, and we can see that being printed out here on line 11. So that is going to be this value here. So this value is actually going to be this here, right? So, I mean, these two memory addresses match. Now, what's happening here? So we have here we have a output as well that is outputting it's supposed to be outputting an integer, and we're dereferencing our address at X, our variable value stored at X. And you can see that we're kind of getting this weird value here. Now, what's occurring? Well, what's probably occurring is that there's some conflict of type because it's not reinterpreting it. So what we probably need to do here is reinterpret this as a character pointer here, like so. Rerun, and there we go. So again, just using the typecast with our particular pointers helps us out to dereference this into the value that we expected. If not, it will interpret this data in an obscure manner, just because it's not necessarily what you may think it is. So to provide further context into this, let's go ahead and make another integer, an explicit integer, since our actual X variable is a pointer to an integer. So what we're going to do now is we're going to reassign x to the value, to the address of y. And we're going to take this same line here and just kind of edit this. And all we're going to do now is just deref y. And let's see what this output is. Oh, sorry, not y, x. Right, because we don't want to dereference our non-pointer type. That's all that was complaining about. And we can see that everything works as expected. Again, because this wasn't recasted, there is some type of obscureness going on here when I dereferenced it. It's not what this expected. So it's important to, if you get weird results like we were expecting, just remember that we need to cast it to that particular type and then reinterpret it by dereferencing it. So that is exactly what's happening in this particular line. And if you want to be incredibly explicit about it, you can wrap these even in more parentheses, however you want to accomplish the task. Now, in order to get rid of this warning, what you would do is you would actually cast this to a particular integer type. And that would probably actually solve this problem down here. So what we're going to do is we're going to go ahead and say that this address now is actually a pointer to a integer. Let's see, something like this. Let's see if that fixes our issue. Now this may also still complain. Well, not necessarily complain. There's going to no longer be a warning, but you will see that now it's still some obscure value. So what we want to do is still just make sure that we're reinterpreting it as the appropriate type. And this is probably because a character is typically an unsigned char, you know, depending on what's going on here and how it's interpreting the actual bits. So anyways, I hope this gives you some better insight into how to like do some typecasting with dereferencing. This also eliminated the compilation warning, because I was explicitly telling the compiler that I want this to be interpreted as a integer pointer, so that way that warning would go away. You can see it didn't really affect the code here. We don't necessarily need to worry about that. In order to fix this, we would have to do some type of other type of casting. It's again, this is not necessarily, you know, quote unquote fixing things. It's just not being, you know, not having to recast and do all this craziness. So hopefully this gives you an insight into how to use pointers and how to dereference them. I think that this one is probably, this shows you the importance of making sure your pointer types match, so that way you don't have to keep mangling things up, like doing several casts and dereferencing. All right, great. So thanks again. Hope we'll see you in the next lecture.